I think, thank you very much for coming to this month's CAPE Advanced Lecture. I'm Daping Chu, I'm Director of CAPE. And this time we're very honored to have Dr. Wei Zhang to join us, give a talk. Dr. Wei Zhang received his PhD degree in computer science from the Chinese University of Hong Kong and in 2010. His master's degree was from Tsinghua University in 2005, and his bachelor degree is from Nankai University in 2002. Dr. Wei Zhang joined Huawei in 2012. Before that, he was an assistant researcher in Shenzhen Institute of Advanced Technology, Chinese Academy of Science, and also in the Chinese University of Hong Kong. Currently, he's the director at Huawei Technology Research and Development UK Limited. He's the director of the Huawei Technology Research Center in London, and he's also a co-organizer of the self-supervised learning for next generation industry level autonomous driving, and the workshop at the ECCV 2022 and the ICCV 2021. The title of his talk is DetClip. I hope I got that right. DetClip, Scalable Open Vocabulary Object Detection via Fine-Grained Visual Language Alignment. Dr. Wei Zhang, please.
Professor Chu, it's my honor here to give such opportunity to share our recent research on the AI, especially. Very fundamental, the computer vision. Okay, so let me share my screen. Okay, so before I start my presentation, here is a very brief introduction of my current organization. So far, I was in London Research. This research center, established maybe 4 or 5 years ago, and so far we have around 50 people engaged in the AI-related research. Currently, we are at the research center that focus on the following 5 directions. The first one is the theory part. We focus on how we can modeling the generating signals. It can either be the image or can be the text or either be different type of signals. And we also have the reinforcement learning theory team, which we focus on the optimization theory and also the multi-agent reinforcement learning. We also have the NP team. Here we focus on 2 things. One is the dialogue system, which is very common and highly frequently used in our daily life. And we also focus on AI for software engineering, highly related to the, the dialogue. And also for my part, I'm in the computer vision, branch, and we focus on 2 things. The first one is video ISP. I think, for our video thing there currently, to make our video quality to be better, we need to have the basic fundamental, ISP processing. So another thing is about 3D vision, how we can understanding the whole 3D world in our, indoor or outdoor, environment. That's the main topic I want to share today. And the last one is the neural computation. We do some, inspired computing, which is quite related to the by neural network, something like that. Thanks for Professor Chu. I think some of my topic maybe have some little overlap with the topic here in CAPE. So since we talk about 3D vision, part of my presentation is related to the how we processing the signals from the LiDAR. Very quite important for the both the robotics or autonomous driving. I will share in the later part. Okay, the first part is a very brief introduction of the background. So what's the definition of the visual language pre-training? So it's a very important research topic here in the computer vision that we leverage both domain knowledge from the NLP and from the image to learn the robust feature representation so that it can be used very well. Different vision tasks, like how we can detect object from image, how we can understand the meaning of an image, something like that. So here are some examples. Yeah, so what's the task we want to do? Okay, you can see the pair of image and the related text annotation, which we call the pair of the image and text. So given such pair, so it has a related correspondence between the content of the image with the related the annotation. We want to learn the robust feature representation from both modalities. Yeah, so they can align quite well with each other. Yeah, so such alignment can be done by using some data-driven approach. So far in the AI community, we use some neural network to achieve that. So for example, in the left part, it's a very common filter dark one. So for example, for an input image, we can do some processing like using a transformer to do some basic information processing and extract the vector-like feature representation. And similar things can be done for the text part. And with the feature extract from different parts, we can do the alignment and to do using some matching laws to determine whether or not their semantic are align or coincide with each other. Yeah. So based on the learning, sorry about that. Based on the learning, so we can have a very robust feature representation that can have the correspondent meaning from both visual and the text part. So it has very widely usage in our daily life. For example, we want to do the query or search from the web search engine. So we can just text the text promote and using the extract NLP features to find this corresponding image feature to do the image retrieval. Yeah, so the performance is much better than the traditional approaches. Yeah, so besides the image or text retrieval, we can also do very more application. For example, we can do the image generation based on the text input. What we call text to image synthesis. So currently hottest topic here is stable diffusion. I assume part of our audience are quite familiar with that. You put some promote and generate corresponding image that can have a semantic semantic meanings as that. So that's part of the potential applications. But that's not my focus of today. Today I want to show this alignment of the text with image can also have more applications in some fundamental computer vision tasks. For example, we can use that for the image detection. So image detection is very fundamental, CV tasks for us. So generally, given an input image, we want to locate, give the exact location of the target we want. For example, we can input, for the sofa or for the cat, just give the text input. We want the algorithm or neural network try to know or learn how to localize the location of that. So that's what we call the object detection. So this is quite fundamental, but that's very hard. Yeah, after a long time of research, we found its limitations. What's its current limitation? So far, we need to do the object detection in a supervised learning setting. That means we need to have labeled training here for both the image and its annotation. For example, if we want to train a detector for the cat, we need to have bunch of the image, have bunch of annotation, which cost quite high. Yeah. And it's also done in a supervised learning. Yeah. So we need to have a period of the training sample and try to learn that. This very, the positive, but the generalization capability is not quite good. So it relies on sufficient training for each category. Yeah. And also not fit well with the current situation. For example, in our, the delayed life, when we want to do the robotic or do the, autonomous driving tasks. Yeah. In the open environment, you always need to identify, detect, or localized object that may be not in your training set. For example, in a freeway or in a highway, there is a broken tire, on the road surface. Yeah, you need to identify or localize that object in a quite efficient way. And you cannot get too much, training sample of this type. So for the traditional supervised learning, yeah, so it's a challenge task how to do that. Yeah, so we need some, open set object detection. So that's what the topic for today's presentation. We want to do the open set detection that can do the detection on the object or the scenarios that out of the previous, defined training set. So that's our motivation and what's our current situation. So we can easily find, the lots of, low cost image and text pairs, yeah, from the internet, and we can using the visual language pre-training, yeah, to learn a very robust, feature representation, yeah. So this feature representation can serve as a, prior to get it your object detector to have a, very good performance and have very good near shot generalization abilities that can do the open environment detection. So that's my purpose. Okay, to achieve this goal, what was the data set we use here to achieve that? We have the diversity of the data set we can gathering or collect from the internet. The first time of the data set is a traditional detection data set. We have the the bunch of images. We hire some human annotators to do the annotation with very high cost, but the amount of this detection set cannot be very large. And we also have a very large, the image or text pair there from the internet, because from internet you can record lots of, thousands, even, millions, even billions of the images, which you can have the tag or the related text annotation. Yeah, so with very low cost. And the label here, they have the, the costly semantic alignment from the image and from the text, but you cannot find the precise semantic correspondence between them. And there's some, insight, in the middle of these different types, we call them visual grounding data set. For the visual grounding data set, we have the, the image and related, text annotation or the text description, but we also have the semantic alignment with, the key concept in the NLP, and it's, related object or localization in the image part. So the cost of this, grounding data set is, between the detection and between the detection data set and the image text pair, and but also the available amount of data is also between them. How we can leverage this different type of data and to do the open data set, open site object detection. So that's the main thing I want to share today. So as beginning, yeah. So since we have different types of the the image and text pairs, we need to have a unified representation and formulation of these things. So first, we need to get unified formulation from the text things. We call that conception promote. So what we do for this part, we propose a parallel formulation for all the the non-phase in the concept, which can have the exactly bounding box correspondence, and we build the pseudo label this two side, try to give the unlabeled image text pairs here to give their very coarse object bounding box, and build the coarse correspondence between the text pair and the so we call this the pseudo label proceeding. With all this data processing pipeline, we can have a unified data representation for the above mentioned three types of data set. So why we need to have the concept direction for these things, because for the diversity in the site, for the exact same annotation, they have different meanings. But for example, you use two examples in the lower part. A motor, it can be expressed with four view things, but it can also be explained with the two view things. So different concepts, they have different semantic granularity. So for the different types of the granularity, they maybe have some ambiguous in their concept. So we need to build a concise and uniform conception, because with this unifying conception, so we can easily to processing the NLP part to have a robust NLP feature representation. So to do this, we construct a very large concept dictionary from the internet part. We extract the non-phase from the even the millions or billions of the image text pairs. For example, we built around 40,000 concept, and for this concept, we try to get the exact non-phase and the related text presentation. The examples how we make this concept dictionary. For example, so the non part for cup is the related definition. So it's a small open container usually used for drinking something, blah blah blah. It's something like a key, and value is the definition of the whole concept. So all these things are extract from the previous mentioned data set. For the detection data set, we can have very precise concept. It has a carb, chips, chair. These nouns can be used as labels, and we can also extract from the very low cost image text pairs from the internet to extract the definition. So we set up the mapping between the concept and the definition to do the concept formulation. With this unified formulation, so we can leverage all these sets with the same semantic understanding level. Okay. So to enrich the conception dictionary, so we do the conception enrichment. How can we do this? Just mentioned before, for the different types of data set, for data set, we append our previous extract the semantic information, the definition to the previous the concept, and to construct a enriched representation from the text promote. When we built unified representation from the NLP part, we have a very robust alignment concept, and it can be easily to do the feature extraction from the NLP modality. And this is the data preparation for the training from the NLP part. And on the same way, we need to do the pre-processing for the image part, what we call the partial annotation problem. What we do here, the main purpose is that we enrich the concept of all the target that we are interested. We build a concept dictionary with around 40,000 with 14,000 items. We also need to do some data strengthen or data augment for the image part. How should we do that? We do something like this. Yeah, for example, for the input image, we need to extract all the possible objects we are interested in and enrich them with the learned concept dictionary and add the pseudo label for them, which we call the label creation and the partial annotation enrichment. What we do for this part, for example, this is a previous input samples from a detection data set. We have an image, we have the high cost human annotation like chairs, like desk, blah, 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 all these things. But we also do something. We want to, do the data annotation and automatically, add the pseudo label for the other concept. How can we do this? We do this by using the previously mentioned. We do the semantic alignment of the image and the NLP representation. Then we have some robust feature representation like GLIP, to extract some fundamental alignment seen there for this image. For example, we can possibly split all the image into different types of grid. For each grid, we try to find the most related semantic part into the for this patch and give it an initial label for that. That means for all this semantic part in this image, semantic component in the image, we try to find the related semantic label for these regions. Yeah. For example, for the previous image, we have three annotations like it's a child maybe and laptop and the further thing there. But we can also add desk or all these things there based on the previous pre-trained language model and and the pseudo label for that. With this data augmentation for the image part, we can automatically strengthen the feature representation from the image part. All this pre-processing step, we have the concept detect, we have the concept dictionary for the NLP part, and we also have the the partial annotation enrichment for this image. With all these things, we can have what we can have here is that for the image, we can automatically extract its feature representation and with the course label, and we also have the the concept dictionary, which can enrich the whole text with the related the semantic meanings. Here we can have all the concept that is enriched or in this image, and we can also have the related annotations of the box from the previous page. So we can have the alignment, then we can have the localization and have the regression. So all these are combined together to make sure for the extract image representation, we can have semantic alignment here from the concept direction, and we can also, if there are some precise localization, we can also do the localization learning for the bounding box. So this is all the architecture we want to do for our, object detection, with alignment of the RP. I don't want to, to give you some, theory on this part. But what we want to do here is that with this training, and when you input an image here, it can automatically extract the image feature and try to find the corresponding concept from the concept direction. So for example, if you have a huge, concept direction with, over 10,000 concepts, it can, do almost all the detection, with almost, the delay use concept. So that's the method we use here to do the open set detection. I don't want to, mention about this number details, but I want to say, we use a huge, we use a very huge data set to achieve that. For examples, we use, the huge LVIS data set, which have, the concept of the detection as with over 1,000. So, and this data set gives us very precise annotation of the concept, and it also is corresponding bounding box. And we also leverage some, pre-trained CLIP, which is trained with billions of the image text pairs to give us the concept over 1,000, over 14,000 concepts. With all this together, so we can do some, very good performance on the open site detection. I just want to show what's the concept of open site detection. So this is a delay captured videos here. So you can see we can precisely localize all the concept, all the entities in this video. So we just give one example, and it can also do very well for the outdoor scenarios. So. If all the concepts can be covered by the above mentioned, when you can send a very large concept dictionary with the leverage of the very low cost internet image and the related text pairs, for example, you can get this concept, so many concepts with 14,000. You can do the annotation or detection for almost all these 14,000. That's what we call the open site detection. This can also be applied for the autonomous driving when we want to detect the fire or something. So it can be easily covered by this thing. Also, if some concept is not covered by the current settings, it's easily for you to add new concept with text mode and then add few samples and fine-tune the whole system. So it's a quite extendable framework to do all these things. Sorry about that. So I want to extend this idea to the 3D. 3D, what I want to mention for this topic. So we want to do the open world, open site, point cloud presentation. Why point cloud? Point cloud is one of the very important data format we used for different robotics or driving tasks. For the cars, when you set up with LiDAR, easily to get the point cloud for the outdoor environment, and you can easily understanding that by annotate, give the semantic label for each point, whether or not it's an obstacle, it's a good service or something like that. So just like the examples here, and you can also do the indoor perception with the point cloud, equipped with the robotics. So. But we face a similar challenge to do the open site detection for the 3D signals like point cloud. But I think the challenge is even harder because for the image for 2D things, we can leverage the low cost image text pairs from the internet. But that's not true for 3D. It's hard to gather ingredients of the point cloud and with low-cost text annotation there from inside. So how can we do the offset 3D perception with the leverage of the previous framework? So here is our solution. We want to be using the 2D low-cost 2D image and the text as an agent, and reduce cross-modality element together with the text and also with the cloud, point cloud, and also with the image. We want that have the correspondence among these three modalities. So with the huge knowledge, and we learned from the text and image, correspondence, we can borrow or transfer the related knowledge into the point cloud part. So that's our policy here to do this. So to do that, yeah, we have the same things. We do some preprocessing, yeah, to construct a concept dictionary for all the point cloud, and we do the related to the annotations, yeah, from the image, and we also have the the point cloud, which has the related that annotation, but the amount of the cloud is much lower than the related image and the text this side. So yeah, so we use the cross-modality training or alignment here from these different modalities. The first one is that we also do the feature learning or feature extraction from the concept, and we do the feature extraction from the correspondence image, and with precise alignment. I mean, the alignment here is that for each point cloud, its correspondence between the image pixel and its 3D location. So we do the point cloud feature extraction. Then we force the extract feature representation should be alignment in the concept or in the semantic feature space. So that's what we do. We do that in the learning session. That means for the same concept, we try to make them to be more closer to each other. For next thing, we want it to be disparate from each other. Then after the alignment, so we can easily transfer the semantic knowledge from the image modality to the point cloud modality. Then, for the test, when you input the concept, we can easily find the related corresponding part from the outside. So here is a very traditional, typical scenarios. For the the indoor the cloud data site, when you input the text mode with a key concept like sofa or paper or desk something, so we can easily do the traditional object detection in 2D, but we can also leverage the image and point cloud alignment. We can also identify the precise location in the point cloud space. So that's what we call the open set point cloud application. So our proposed method can achieve better when leverage with the huge amount of the text image pairs, and it can huge performance improvement of the concept. So this for the outdoor environment, this is typical of the very famous benchmark data set for the learning. You can have pairs of the you can have pairs of the image and the correspondent point cloud. So when you input when you want to localize something, for example, if you want to localize car, that's the motorcycle, you just input the concept, and then you can easily do the localization in the image modality. That's what we call the object detection. For motorcycle here, you can easily find the correspondent point cloud. So So that's a typical way where we do the the 3D point localization. Yeah. So for the input, we input the raw of the point cloud. 8 seconds, and we input the calibration parameters. Yeah, to make sure we can find the exact difference between these two modalities. Then we also have outside input is the input of the target classes, which we also call the concept. The concept can be open set. With the input of the target class, we can output the correspondent labels in different modalities. So the advantage we said, we don't need extra human cost for 3D annotation, which is key challenge for the current, AI or the computer vision technology to be expanded to the more scenarios. And we can also have the free class extension. And so this is very useful for the typical scenario if you want to extract some, valuable corner cases or valuable, the real cases, from the real sightings. So this video shows one of the typical example. We want to detect some real scene, object. For example, we want to detect the white smoke. Here to see, we can just input the concept and let them do the semantic element in the image and in the point cloud modality and find related. Do for the spring water. Something we want to do. It's hard to gathering if you want to instantly find something on your delay and gather data, but you can leverage the concept learning from the text to image correspondence, and you can easily transfer the related semantic to the cloud mode and validation. For that. This just shows two of the very typical unseen object in the daily life. So I think I want to share this work just because it's very fundamental. When you can do something like the open set perception, it means that you can easily to do the visual understanding with very low cost. When you add some new concept, you can learn very easily to learn from the text modality to the image modality, and then find the correspondent. Then you can do the very low cost, and you can using it as a fundamental tool to do the pre-processing when you do some new vision tasks. So this is my take-home message here. So currently, we do some fundamental computer vision research that we call that visual language pre-training, and it can benefit a lot from the visual language pre-training, and especially in the dear short we call the open set setting, and we can also think multimodality learning can be strengthened with leverage from text image matching, which is easy to turn from the internet. I try to make a summarization here. That's all for my presentation. Thank you all.
Very much. Does anybody have any questions on that very interesting talk? Anybody? Question in the room. Excellent. Questions for the 3D video open set learnings. When you're trying to align the features of 3D with languages.
Exactly.
So you're saying there's not enough data set pairs for you to do that. So I imagine you are using 2D image as a bridge. So can you elaborate on that? How did you actually do that?
That's a very good question. I don't go very deep into details. I like say, just like the 2D, offset detection, like DetClip, you can build a very strong correspondence between the text and the image, right? But you have lack of the the link with the point. So how can we leverage the knowledge from the image channel? And so we use a pre-trained DetClip and fix here, to it as a fundamental based on a model. Yeah, so you can find the content image. Then for the new edit point cloud, we just to train and find the alignment between the text encoder and PC encoder. So it's just like something we have already exist this text encoder and the image encoder. We can have very well alignment.
It's quite similar to ScanNet 200, that papers. They were doing quite similar things.
Yeah, maybe, but something here is that we think it's quite fundamental. Yeah, so it's quite a new technology. Yeah, maybe different groups have similar ideas. Yeah, I admit this is not something quite complicated. It's something quite straightforward, but it's very useful. Yeah, from outside, I think our novelty is that when we train the point cloud encoders, so we enhance the prior knowledge in different ways. Yeah, you can see maybe for the loss set it be quite similar with the ScanNet or something. But how to modeling the knowledge, how to add a constraint to let the point cloud feature to be aligned with text or with the image encoder. Yeah, so we have different way to modeling that.
Yes, thank you.
Question? Chat. Yes.
That's
okay.
Okay, thanks.
Okay, well, let's all thank our speaker again. And thank you all for attending.
Thank you. Bye-bye.
To be here. Thanks, Ed.
Bye. Have a nice trip, Michael, tomorrow.
Thank you.